Okay. So, what? Oh, if my internet is slow again today, I'll be so mad. It was so slow yesterday. My screen kept lagging. Like, and I'm plugged in. I don't know. Just can't win. Oh shoot. Now I've forgotten if I hit record or not. I am recording. Well, I never edit my videos. I would probably cut that out if I did. All right. So we're going to start a new type of question today. And so one of the hardest parts in statistics and data science is figuring out what type of question you have so that you can know what an appropriate analysis would be. And so we've only talked about one type so far, and I'm going to call it one sample proportion. And we used it to introduce ideas about confidence intervals and hypothesis testing, decision errors, right? Those kinds of things. But now all those skills, we'll use them again for the new type today, which is two sample proportions. Which means that I'm going to have two different samples, so two different groups of categorical data, right? So here, two samples of categorical data. And we want to compare the proportions in each group. We want to compare the proportions in each group. Okay, so just as a little bit of review, because we're going to rely on it today, previously on DSCI 228, I guess, for a confidence interval, just in general, to build a confidence interval, so many colons, I need to cool it with the colons here. For a confidence interval, underline, there we go, how original. We have some point estimate plus minus some critical value and times the standard error of the point estimate. Okay. Now for one sample proportion, I can't help the colons, I guess. The point estimate, my best guess at what the population proportion was is p hat. Right, so we built our interval around our sample proportion, and then we had some plus minus a critical value, which we denote by Z star, right? The Z, so we tell this, where's my pointer? Here. We tell this interval how many standard errors we want to move out, and that dictates our confidence level, right? And so Z star, we said, well, let's just use 2 for simplicity, right? Because we'll just build 95% confidence intervals. Technically, it's 1.96, but close enough, right? And so we're just doing rough approximations, but you can use Excel or any other software to find the proper critical value. And so as I say that, I'm realizing that the assignment I posted might make you work for it a little bit. Let's see here. So I did post, I wasn't sure what to call it because it's not a Friday assignment. It's just an extra assignment to practice the theory. And so let's see here. Let me go to our Moodle page. And just I'll stay in instructor mode. It's going to look pretty messy here. Blah, 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 blah. Here. So I posted a week 9 assignment. Like I said, I wasn't sure what to call it. And just for some theoretical practice, right? Especially because you've got the theory quiz coming up on Friday. So it'll open on Friday and stay open for the weekend. But this is what you'll want to practice. Okay. And there's how many? There's 12 questions. But some of them are itty bitty. Some of them are long, some of them are itty bitty. Okay. And like I said, I'm just realizing here it's asking for a 99% confidence interval. How would I do that? I can't really remember if we did it. You're going to use equals norm.s.inverse, and it takes the area to the left. So if you want a 99% confidence interval, then you want 1% in the tail, right? And so this area then, all the way to the left must be 0.995. Right? Yeah. 0.01 divided by 2. Yeah. So then for 99% confidence interval or confidence level, Z star is norm.s.inverse. I think it's like 2.576. We had to memorize it. Back in my day of 0.995. In fact, let's try it. Equals norm S inverse of 0.995. Hey, 2.576. Close enough. Okay. I did it. Which equals 2.5758 ish. So you can find any confidence interval, right? But as a default, we'll just use 95%. But yeah, that was an oversight on my part. It asks for different confidence intervals, so it's good to know. But in life, you're going to use 95%. And then we said the standard error of the point estimate. So the standard error of p hat for a confidence interval is p hat q hat over n, square rooted. Make it not so big. There. So now, today, kind of new, for 2 sample proportions, just so we can see how they line up. 2 sample proportions, the point estimate, actually, sorry, we're not ready for that. Sorry. Nope. Haven't even introduced what we're trying to analyze. Let's go back here. I'll call that the end of the review because I'll introduce the confidence or the hypothesis testing as we go, but just remembering the point estimate and the standard error of the point estimate is a good place to start. So what we want to do is we want to compare the proportions in each group. So now I'm going to have some P1, right? The population proportion in group 1 versus P2, the population proportion in group 2. Now, if I asked you to compare these mathematically, your go-to would probably be what? Well, probably looking at the difference, right? How far away from each other are they? So to analyze two proportions, and maybe I'll say how two proportions compare. Right, P1 versus P2. We consider the difference. We consider the difference. Right, P1 minus P2. You could do P2 minus P1 if you want. The 1 and 2 assignment is arbitrary. It's just, you got to stay consistent in your formulas later. Okay, so it doesn't matter, but as long as you're consistent, right? If P1 is less than P2, then P1 minus P2 gives you a negative, right? So it's centered around a negative value. If P1 is greater than P2, then P1 minus P2 gives you a positive value, but the distance between them is going to be the same, right? And so then your interval is just going to swap, okay? And so here, I'll make a note. The assignment of group 1 and group 2 doesn't matter as long as you're consistent. So what we're going to be hypothesizing about and building confidence intervals around is P1 minus P2. We're trying to figure out what P1 minus P2 looks like in the populations, right? And so, well, let's think about what our point estimate would be. I'm trying to figure out what P1 minus P2 looks like. Well, my point estimate must be P1 hat minus P2 hat. Okay. So that's good. Now, just as a fact, the distance between these two proportions is also going to follow a Z distribution, so a normal distribution. And so the critical value is going to still be Z star, right? It's going to be 2 for a 95% confidence interval. But we need to figure out what the standard error of the difference in the proportions might be. And so for a confidence interval, I'm just going to tell you, for a confidence interval, the standard error of P1 hat minus P2 hat is going to be this. Oh, sounded like, is it on the speakers? Oh, bless you. I just heard something. P1 hat, Q1 hat over N1. Hey, that looks familiar, right? But the problem is I have information from two groups now, right? And so what happens is I need to incorporate P2 hat, Q2 hat over N2. So it makes it look a lot bigger, but not too crazy. The unfortunate part is there's no built-in functions in Excel where you can give it your sample proportions and your sample sizes. You would have to build it yourself, whereas later we're going to have built-in functions where you just give it some information that it needs and then it spits out the probability or the test statistic. And so that's going to be nice, but for proportions, it doesn't. I haven't found it, and I've looked, so I conclude it doesn't exist yet. I'm sure they're working on it. And so now, right, what information do we need? So now we have information from two groups. Right, so we have group 1 and group 2. Let's think about the information that we needed to solve. Let's start with a confidence interval. A confidence interval for one sample proportion. Well, I needed to have n. All right, so group 1 has some sample size n1, and group 2 has some sample size n2, of course. We needed to have potentially x. X is the number of successes. So group 1 has some number of successes and group 2 has some number of successes. Let's just say number of successes, just as a reminder. And of course we needed p hat. Well, now I have a p hat for each group. P1 hat is x1 over n1, and p2 hat is x2 over n2. Sometimes the question gives you the p hats, but you need to find the successes in order to check your assumptions, which we're not focusing too much on, but just a little bit. Okay, so let's see here. We have the point estimate. We have the standard error of the point estimate, and the critical value stays the same. So a confidence interval for one sample or for two sample proportions, the confidence interval for two sample proportions is going to look like this: P1 hat minus P2 hat plus minus, and that's all one value, plus minus Z star, which is the same as before, times the square root of P1 hat Q1 hat over N1 plus P2 hat Q2 hat over N2. Bink. Just look like N2. So now, when we're interpreting this confidence interval, we're going to interpret it in terms of the difference in the proportions. Okay, because we're talking about how P1 minus P2 behaves, right? And so that's good, but you'll also be able to just steal that from the question, because the question will have to ask you to build a confidence interval for the difference in the proportions, whatever proportions we're talking about. Okay. Let's do an example. Got one in here that I like. Whoops. Guess I'll, you know what? I'm gonna see if I can just copy, select one, select 1, 2. Don't like these. Sure. And that one. Copy. Bring those in. It is cheating, I know. Paste. but I won't make it this big. That's crazy. So we're going to be talking about this example where there was a survey and they asked, or they said, scientists predict that global warming may have big effects on polar regions within the next 100 years. One of the possible effects is that the northern ice cap may completely melt. Would this bother you a great deal? Some, a little, or not at all if it actually happened. And so here are the responses. This is categorical data, right? Categorical data. Each observation is going to select one of these options, and the results were like this. Bless you. And add a page. And may as well delete that one. Okay. Where did it go? Just put it here. This talks about the GSS. The GSS, I think, is the General Social Survey that they do in the States. So we think of this as all Americans. So that GSS survey represents all Americans. They take a random sample and ask them these questions. And so it asks the same question, below are the distributions of the responses from the 2010 GSS, as well as from a group of introductory statistics students at Duke University. And where I stole this from, one of the authors teaches at Duke University. So all her examples are about Duke, which is kind of fun. So here are the responses, right? And so we have some count in each category for each group, right? And so, and then we have a total sample size, right? And so if we let this be group 1 and this be group 2, right, let's start there. And because I know what we're about to talk about, a success is going to be those who answered a great deal. So that's the proportion that we're interested in, right? And so is there a difference in proportions of people who answered a great deal in all Americans, yikes, versus the Duke students? Okay. And so we're going to consider this a success, which makes this a failure, this a failure, this a failure. We can zip those up into just not a great deal, right? So we can ignore all those categories. Sometimes when we're just starting out, it's kind of confusing to have multiple categories, but depending on the question, you'll need to figure out, okay, which one is the one that I'm interested in? And then all the other ones are failures, right? And so here, these are just not a great deal, which I guess could also apply to like a sale item or something. But we're going to call these all failures. Okay, I'll use this guy. So we had that information that we needed from before, right? We said we're going to need and, we're going to need x, and we're going to need p hat for each group. Group 1, group 2. N1, group 1, N1 has a sample size of 680. N2 has a sample size of 105. Have it there. X is the number of successes. X1 is 454 and X2 is 69. And P1 hat is 454 over 680, and P2 hat is 69 over 105. Okay. So you could organize your spreadsheet this way, right? And then reference the cells to keep all your decimal places, right? Because we are going to build a confidence interval. In fact, where is it? Oh. Grab that later. I want to swap these. Oh, keep forgetting it's in the same document. The proportion of Americans and Duke students who would be bothered a great deal by the melting of the northern ice cap. Why did I make that change? Well, just because I want to do group 1 minus group 2. Otherwise, I'd have to do group 2 minus group 1, and it gets confusing. And so I want PUS minus P Duke. That's the only difference. Nothing crazy. Okay. Because now I can talk about group 1 and group 2 generically. Right? And so if I want to make a 95% confidence interval, right, for the difference between the proportions of Americans and Duke students who would be bothered a great deal by the melting of the northern ice cap, so it tells you the difference that you want to investigate, then a general confidence interval, or we already did it actually. Let me grab it here. Looks like this. Copy. Paste. And we have our P1 hat and our P2 hat. In fact, let me grab my calculator. Wait. I probably do this in Excel if my numbers didn't show up so small. And it's kind of hard to type on the iPad, but I don't know. Let's see here. 454 over 680 is, I'm going to round to 3 decimal places. But if you were working in Excel, you'd be able to keep all your decimal places, and that's nice, right? And so 0.668 rounded to 3 decimal places. And then 69 divided by 105 is roughly 0.657. Okay. So now I have P1 hat and P2 hat, and I have N1 and N2. Because I have P1 hat and P2 hat, I also have Q1 hat and Q2 hat, right? Because they're just 1 minus the P's. And Z star, we're just going to use 2 for a 95% confidence interval. Or if you're using Excel, you could find a better value or use Excel. And it should be Z star is equal to 1.96-ish. But for simplicity, we'll use 2. Okay. just looking at these proportions, right, 0.668 and 0.657, those look relatively similar to me, right? But what I want to know is, okay, are these different enough to be considered significantly different from each other? That's what we're building up to, right? And so I'm going to look at this and figure out what my confidence interval is first, and then I'll remember that it's for the difference in the proportions. So here we go, 0.668 minus 0.657. And I think I'm going to need more room. Wait. On that page. Plus minus 2 times the square root of 0.668 times 1 minus 0.668 divided by n1, which was 680. So many 6s and 8s. Plus p2 hat, which was 0.657 times 1 minus 0.657 divided by 105. That's kind of tedious, especially on a regular calculator, right? And so one kind of cool thing that you could do is you could set up a bare bones spreadsheet to calculate two sample proportions, right? And so all you would need is a box at the top where you change these values, right? And then as long as you have a Z star somewhere being calculated, because that might make it easier, then as long as you reference all the cells, right, that you want, right, then it'll just adjust it as you change your X successes and your N's, right? And so that's probably worth playing around with and making sure that you've got it set up, because then you just need to make changes, right? The goal isn't really the calculation, it's to introduce you to the calculation, but it's more in the interpretation, right? And so I guess if I were you, I would have a spreadsheet with little tabs, right? 1 sample proportion, 2 sample proportions, and then you can have them all set up already. That might be nice. And hey, what a good idea. I'll make you do it. I'll set up some instructions probably. Okay. Let's see here. Plug and chug, I guess. Did I have it? So because oh, well, now that I see it here, tomorrow is Pi Day. Okay, where did it go? There, a little break. Tomorrow's Pi Day, so enjoy. Pretty funny. Little bit funny. Okay, but I was going for a calculator. Okay, clear all. So I wanted, and let's see if I do this, and it's still showing me, right? You can see both, sort of, kind of tiny. I can see both, which helps. So I have 0.668 minus 0.657. I would have had these pre-baked, so to speak, except yesterday when I did this example in my other class, I had a typo that I didn't catch, so we'll start fresh. This is my point estimate, and I'll call it P. Oops. because it's my point estimate. Now what I want to do is I want to take the square root and just be really careful about 0.668 times 1 minus 0.668 divided by, whoops, I guess it still works, but I want it to look better. Divided by 680 plus, oops, no, plus has to stay under the square root, bracket 0.657 times 1 minus 0.657 divided by 105. Hey, we did it. This is the standard error, so I'm going to call it S. Hopefully I didn't make a typo again. Looks okay. Doesn't mean I didn't. It just looks okay. So now I can refer to, so this is the Desmos scientific calculator, which I really like because you've got the line display, you can store things, which you can on many calculators, but it's just nice. So for my lower bound, right, I'm gonna have P minus 2 times S. And for my upper bound, I'm going to have P plus 2 times S. So here, my interval then, I'm just going to jot it down, becomes negative 0.088. Sure. I'll screenshot the other one and bring it in. But 0.110. Bring this in. Hey. Okay. This is for the difference in the proportions, right? So the difference in the proportions goes from a negative number up to a positive number, right? And so usually what we want to know is whether the difference in proportions shows that they're significantly different from each other, right? And so something to think about when we're talking about the difference in the proportions here, right? If the difference crosses 0, right, going from a negative difference to a positive difference, then that's proof that they're not significantly different from each other. We're 95% confident that a difference of 0 could very well happen, right? And so we need to interpret this interval, and we're going to use the exact same blurb that we used before, just remembering that now we're talking about the difference in the proportions. And so we are 95% confident the interval from negative 0.088 to 0.110 captures this is where you rephrase the question as an answer. So we were asked to build a 95% confidence interval for the difference between the proportions of Americans. I'm just going to copy this and I'll write it out and then I'll delete that. So captures the difference between the proportions, oops, only because that copy paste looks so messy. Proportions of Americans and Duke students who would be bothered a great deal, blah, blah, blah. Oops, bothered a great deal, right? The success by the melting of the northern ice cap. What's nice is I'll get you to interpret confidence intervals on the quiz, but then it'll just be a text box online. So typing it is obviously way faster. You can copy paste and just snag it from there. So it's tedious when we're writing by hand, but not too bad on a computer. Okay, pretty much like everything, I guess. All right, so here, what I want you to think about is there evidence that there's a significant difference between Americans and Duke students in how they feel about blah, 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 right? So is there evidence of a significant difference between the proportion of Americans versus Duke students and copy? Because I can't just not talk about what it is we're trying to learn about, but I also don't want to write it out twice. Who would be bothered a great deal by the melting of the northern ice cap? There. Clearly stolen from above. All right. I guess this is a question. So now, if we want to know if there's a difference in the proportions, then for hypothesis testing, we have to remember that, okay, so first off, I guess I should highlight, is there evidence? Well, this tells me it's a hypothesis test, right? It's that subtle wording that requires a lot of work. And so what do I want to do? Well, if I want to compare the difference in the proportions, and if they're not significantly different, then what would happen to P1 minus P2? If they're the same, then what we would say is that that difference is equal to 0. So that's nice, right? If they are not significantly different. Okay. So that's going to be your null hypothesis. Now, what I want to show you is that we can use a confidence interval to informally test a hypothesis. I feel that eventually kind of research and articles being published and things like that will move towards confidence intervals because they tell more of a story than p-values and the formal tests. But the formal tests are still what we're doing. And so usually we report both. And so I have to show you both. But eventually I feel like we're going to shift towards just using confidence intervals as we're about to see here. Need a page. So we can use a confidence interval to informally test a hypothesis. for example, if we want to test that the null hypothesis is that P1 minus P2 is equal to 0, they're the same until I have proof otherwise, right? And so that's where the null and null hypothesis comes from, is because you assume that there's no difference between the two, right? So it's your no change statement. And so if we want to test this hypothesis, then this 0 is considered our null value, right? The difference of 0. Now, it is possible to test for something not 0, so a difference in proportion being different from 0.1, for example, but that's really, really rare. So usually we just want to know, are they different or not, right? And so that makes it 0, right? And so what we're going to do is if the null value is inside the interval, well, then we're 95% confident that that null value can happen, right? And so if the null value, which is 0 in this case, is in the interval, we do not have enough evidence to reject H0. Evidence to reject H0. Okay. So I like to draw a number line just to visualize it. And I'm going to put 0 here because that's the value that I'm interested in. And then I'll take my interval, which was from negative 0.088 to positive 0.110. Negative 0.088 to positive 0.110. I'm 95% confident that somewhere in this interval, the true difference in proportion lies. Kind of backwards. And so I'm 95% confident that a difference of 0 could happen, right? And so if we had something that looked like this, versus if we had an interval where 0 was here, and then we could maybe have an interval that's all negative or all positive, or, oh my gosh, excuse me, all positive, then we're 95% confident that 0 is not in this interval, right? And so then there is a significant difference. And so here, then we have enough evidence to reject H0 in favor of HA. Okay, so I find that the number line is helpful just to visualize it. But if both your values are positive or both of them are negative, then you're going to reject H0, that there's no significant difference between the two, because then you have evidence that there is. Okay. So we can summarize that by saying, since the hypothesized difference of 0 is contained in our 95% confidence interval, is contained in our 95% confidence interval, we do not have enough evidence to reject H naught. I feel like I said that. We do not have enough evidence to reject H naught. Therefore, the difference in proportions is not significantly different from 0, or what we could say is there is no significant difference in the proportions. Therefore, there is no significant difference in the proportions. I guess I should say of Americans and Duke students. Then I'm gonna steal this. Copy. Paste. Make it blue. And instead of a question mark, period. Okay. Now let me see if we can't see that. Delete that. Okay. I'm going to steal this slide because I don't want to write it out. But we should be checking the conditions. Now, this is more of a theoretical exercise, but it's good to have these things in mind as you're analyzing your data. These things, you'll either have to assume that they're met, or else you can't do your analysis that you want to do. And so sometimes our hands are tied, but let's see here. So we have conditions, and notice that this is just for the confidence interval, but I'll also in pink do a hypothesis test. Because the conditions are very similar. And so we talked about the conditions for one sample proportion, and one of the main conditions was that you have independent observations. And the way that we can ensure that is by randomly sampling. Well, now I have 2 samples. And so, of course, I need to randomly sample each sample to ensure that they are independent within the groups. Okay, and so this is done by randomly sampling. Okay, so we're going to have within the groups, but also between the groups. These groups have to be independent of each other, right? And so usually that's a reasonable assumption to make. And so the US group is sampled randomly, and we're assuming that the Duke group represents a random sample as well. That's not necessarily true, right? But we are saying, hey, I'm assuming that this is how it is, right? And so then this one's optional. Your sample size has to be less than 10% of the population. That's just to make sure that you're not introducing too much of the population, and then they wouldn't be independent anymore. And so, but that's never an issue. And so I say it's optional. And so that's the main thing, is that we have independence within the groups, but also between the groups, right? Still done by randomly sampling. Wait. Okay. These things, these 2 things, are the same for a confidence interval and a hypothesis test. So regardless, you're going to check those 2 assumptions. Now, the success failure condition, which I call the normality condition, or the sample size condition. This is for a confidence interval. And if you have a hypothesis test, then it's going to be slightly different, just in the same way that it was for one sample proportions, right? We had for one sample proportions, for a confidence interval, we had at least 10 observed successes and at least 10 observed failures, period. Now we have two groups, and so in the two groups, right, it has to be satisfied for both groups. Now for a hypothesis test, I'm going to copy this and paste it. Make it a little bit bigger. Move this over here. Versus a hypothesis test. Now we have to have at least 10 expected successes. That's the same as before for the one sample proportion, right? And we have to have at least 10 expected failures in the two groups. Okay. And that's the only difference. And let me see here. Okay, I can delete this one now. So this one depends on what you're going to be doing. If is it a confidence interval, then you need the observed successes. In the hypothesis test, then you need the expected successes. Now, how are we going to find our expected successes? Well, let me tell you. So for hypothesis testing, we already established and kind of worked our way to the null hypothesis. The null hypothesis being there's no significant difference between the two. And so we already worked towards H naught is that P1 minus P2 is equal to 0. And for simplicity, let's say the alternative hypothesis has to be about how P1 relates to P2 still, right? And in fact, how it relates to 0. And so it has to be about 0. And what I'm going to do is I'm just going to talk about not equal to. Of course, you can talk about less than or greater than. It just becomes a little bit tricky because if it's less than 0, what does that mean? It means that P2 is greater than P1, right? And so you kind of have to think about the behavior of P1 and P2 for it to be less than or greater than 0. And so for simplicity, let's just focus on not equal to for a little bit. Okay. This is the same. If you prefer, you could also write P1 is not equal to P2. That's fine. But we are interested in P1 minus P2, so that's why I use this one. But I do find that this one is a little bit easier to read, right? Because, or, oops, I wrote H naught. It's HA, H naught. P1 is equal to P2. Right? Easier to digest, but the theory is going to come easier if we focus on it being equal to 0. Yeah. So that's your null and alternative hypothesis generally, right, for a two sample proportion question. In fact, this will always be the null hypothesis for a two sample proportions question. I do want you to use question specific subscripts, right, because one's going to yield a negative and one's going to yield a positive. And so it matters which one is which, but you only have to do it in your null and alternative hypotheses. So here, I'll say this will always be the null hypothesis for two sample proportions. But we want to use question-specific subscripts, right? PUS, PDuke, that kind of thing. But we want to use question-specific subscripts. Okay. So we do all our hypothesis testing. So this is step one, right? I guess I should have. Step one is state the hypotheses. I don't know why I wrote that funny. Okay. Now, one of the things that we'll talk about, but then just to remember, is that, okay, we do all our testing assuming the null hypothesis is true. Now, if P1 is equal to P2, let's focus on this one for a little bit, right? If the difference is 0, right, those mean the same thing, then it shouldn't matter which group they came from, right? Overall, if I shove all my, and I'm using this for a reason, if I shove all my observations into a pool, then they should just group together. If you're a success, you're a success. If you're not, you're not, right? And so what we're going to use is we're going to use this pooled estimate as our null value. And so that's really kind of tricky, right? But for two sample proportions, we use the pooled proportion to find the standard error. To find the standard error of the hypothesized distribution. Okay. Sort of confusingly, I tend to use p hat. Context will tell me that this is a different p hat. Well, it's not that different, but it is different from a one sample proportion p hat, because I also have p1 hat, p2 hat, and now this overall p hat is going to be the pooled proportion and you could even add a little pooled if you want, but it's going to be, I guess I should write it in words first. The total successes over the total samples. Oops. One way that we could do that is x1 plus x2 over n1 plus n2, right? And so that's going to be your p hat, your pooled proportion. Okay. Or if you don't have, or x1 is n1 times p1 hat, depending on what information you have, right? If you have n and p hat, you can solve it backwards for x. And of course, x2 is n2 times p2 hat, depending on what information you have. But usually you'll have found your number of successes already, so then you can just use those. Okay. So in our standard error of the hypothesized distribution, we're going to use this p hat. In fact, for a hypothesis test, in general, a general hypothesis test looks like this. You have your point estimate, minus the null value divided by the standard error of the hypothesized, distribution for a hypothesis test. And so for us, what we're going to find, and I'm just going to give it to you, then we'll talk about it, is, okay, Z, and it is still a Z, is the point estimate, which is P1 hat minus P2 hat, minus, now the null value is technically P1 minus P2, assuming the null hypothesis is true. Assuming H naught is true, but H naught says that P1 minus P2 is equal to 0. So then this is always just going to be 0. How far is our difference in proportions from 0? Fine. Divided by, and this is what it's going to look like. If you think about the standard error from the confidence interval, right? We had P hat, Q hat, P hat, P1 hat, Q1 hat over N, but now I just use the pooled proportion over N1 plus P2 hat, Q2 hat over N2, but now I just use the pooled proportion. So I have P hat, Q hat again over N2, or if you prefer, Z is going to be, I don't need the brackets anymore, P1 hat minus P2 hat, right? Minus 0, I'm going to stop writing pretty quick here. And what can I do? I can pull out this common multiple and only do it once. It doesn't matter. If you prefer this way, that's fine. But I like to just pull it outside and then do 1 over N1 plus 1 over N2. So that's going to be your test statistic. This is your test statistic for 2 sample proportions. And I guess I'll throw in step 2. I call it do the test. Find the test statistic. How far is your observed sample information from the hypothesized value? And so now, in terms of your spreadsheet, right, your spreadsheet, you already have P1 hat, P2 hat, you have N1, N2, but you need to find your P hat, but that's easy enough, right? Because you can add it to this, where was it? Oh boy. Wow. It's been a while. You can add it up here, right? If you need it, you can have a pooled hat, P hat somewhere, right? Where you're going to take X1 plus X2 divided by N1 plus N2, and then you have your pooled proportion as well. And then you can reference that cell. What's really nice then is that it would change if you changed your X's and your N's, right? As long as you're referencing the cells, which I want you to do. Okay. Wow. What's nice is, okay, we know how Z behaves, right? We know the norm inverse command or the norm.s.dist command to find the areas under the curve. And so now we know how Z behaves. So remember step 3, and I'll throw a smiley face. Hey, that's kind of like an evil looking smiley face. Yay, that's better. Step 3 is find the p-value which is going to be the area in one of the tails or two of the tails, depending on the alternative hypothesis, right? We have a not equal to in our alternative hypothesis in general here. And so then we would have to find the area in one tail and multiply it by 2. And so we can use norm dot s dot dist of z and true, right? Cumulative is always true for the normal because we need the area to the left. Sometimes if you have a positive z, then you need the area to the right, so then you need to do 1 minus. But to find the area to the left, right, and sometimes you need the area to the right, the p-value is the probability, which is an area under the curve, the probability of something as extreme or more extreme than what we saw. Assuming H naught is true. Okay. Is it in? I don't think I have given it to you yet. Did you do the Excel practice for one sample proportions or not yet? Can't remember if where we're at on those, but if you haven't, then you will. I'll post it. Yeah, exactly. So then it'll show you how this norm.s.dist. Oh, okay. Yeah. I think I make you use it a lot, kind of leading up to this stuff because we need it to find the p-values. And then of course the conclusion stays the same. I shouldn't say of course. To me, of course. To you, maybe not so much. The conclusion, you want to compare. So if the p-value is small enough, if the p-value is less than alpha equal to 0.05 as the default, we have enough evidence to reject H naught. To reject H naught, I guess, in favor of HA. And then what that means in terms of the question. Notice here, we said, okay, I can use a 95% confidence interval, and then what's left over, 5%, right? And so that's where this alpha 0.05, 5% being in the tails, comes from. So there's the relationship. And I didn't have that question, but I wanted it. I'm gonna steal it. Blah, 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 blah. Copy that. So for our example, do these data suggest that the proportion of, and we've been using, I'm gonna just do that switch again, Americans, just so we have group 1 and group 2, who would be bothered a great deal by the melting of the northern ice cap differs from the proportion of all Duke students who do. It doesn't matter, but just to match what we're doing here. And then I want us to do a full hypothesis test, because when you see, do these data suggest, right, is there evidence of this, then you're going to do a full hypothesis test. And so we'll do it together. Step 1, state the hypotheses. We've already done that, sort of. Just remembering I forgot to do the conditions. That's okay. State the hypotheses. Okay. The null hypothesis is P1 minus P2. So I'm going to use PUS minus P Duke, like we had earlier. And I have to assume that they're the same until I have proof otherwise. I want to know if they differ from each other. This means a not equal to in the alternative hypothesis. So my alternative hypothesis is going to be PUS minus P Duke is not equal to 0, right? And this comes from here. This makes it a two-sided test. So here, this makes it a two-sided test. There's a disconnect because we don't use that until step 3, right? And so that's hard to remember. But so that's why I write myself a little note. So this is where we would check the conditions, which I haven't introduced yet. Well, we have, but I haven't shown you how to calculate it. I'll just bring this in. Check the conditions. And these, oops, I'll use this color. These are the same as for a confidence interval. So I don't want to do them again, right? I have to have independence within the groups, between the groups. I get that by randomly sampling. I just have to make sure that I don't have too much of the population in there. But what I want to talk about here is the success failure, or the normality condition, where I have to have at least 10 expected successes. And so this we use the pooled proportion to check this condition. Oh my gosh. Sorry. I'm surprised you didn't get ants here. Okay, we'll keep going with this one. I guess on Monday. That's good. I'm out of time. If you have any questions, let me know. Otherwise, I will see you on Monday. All right. Oops.